So for chapter 9, you are going to do 6 practice problems, numbers 10, 11, 15, 18, 25, and 29. Now, let's start chapter 11, rotational mechanics. So for chapter 11, go ahead and open up your textbook to page 150, 150. Okay, so chapter 11 starts with a discussion of the concept of torque. And torque is just work in a circle. And we already have an equation for work. Work equals force times distance. So torque just means it's the perpendicular version of force times the distance away from the center point, a distance away from the pivot point. So torque is equal to force times distance. It's actually reasonably easy. What that means is if I have a longer lever arm, it will exert more torque. So if I want to move something here and I'm having a tough time moving it when I'm up close, make a bigger lever arm. Now I can move it more easily. So the further out you are on the lever, the easier it gets. Great. Let's flip to page 152. Page 152 shows some examples of how to balance torque. And we've already done some of these problems, like the elephant hippo problem, where you have 2 objects on either side of a seesaw, and you have to keep them balanced. So work equals work, or in this case, because the seesaw could theoretically do a full circle, it's called torque. Torque equals torque. And force times distance is equal to force times distance. So in this example, 200 times 3 is 600 Newton meters, or 600 joules. 1.5 times 400 is also 600 joules, so they are balanced. Force times distance equals force times distance. All right, now let's talk a little bit about center of gravity. So for center of gravity, if we want to minimize the torque and maximize the linear velocity, you want to hit something directly on its center of gravity. For example, if I were kicking a football, I want to hit it right smack dab in the middle of the football so that the football moves straight out with no flipping over. Because if I use some of my energy for flipping, that means I'm going to use less energy for direct linear motion. So if I'm trying to kick a very long field goal, for example, I want to make sure that I kick it right on the ball and that the ball maybe spins through the air, but stays straight, not flipping end over end, because flipping end over end means it's not going to get as far. That's also why you throw a ball and spin it so that it stays flat and straight through the air, both to maximize aerodynamics and to stop it from flipping. You don't want your energy going into flipping. Actually, let's show that. So here, I've got my pencil. If I were able to hit my pencil right in the middle, back up a little bit so you can see a little bit higher. It's orange, so hopefully it shows. If I hit it right in the middle, it should go up and come back down reasonably high. A little bit of flipping, but it was okay. Where am I? That was pretty good. Straight up, straight down. However, if I do the same thing, but I hold it at the end and I'm just going to flick the end, it's going to do a ton of spinning, but not go nearly as high. Yikes. Lots of spins, but didn't really go very high at all. I'll do that again. 3, 2, 1. Lots of spinning, very little up and down. And I was moving my hand at the same rate. So I was transferring the same energy. It was just all going to rotational and very little going to linear because I was off of the center of gravity. When I'm on the center of gravity, it goes high, woo, straight up. Cool. So I want to transfer as much of that energy as I can. Since we're talking about center of gravity, your body is really, really good at adjusting your own center of gravity. Let's do a little example. So I would like you can do it with me, to lean down and touch your toes. Okay, so I'm going to show me doing it. Here I am. Are my toes visible? Not really. I'll have to move that table out of the way. There you go. Okay. So when I'm doing this, it doesn't feel to me like I'm doing anything. I lean, I touch my toes, no problem. My body stayed pretty straight, right? Okay, so let's do the same thing, but this time I'm gonna stand up against the wall. You try it too. So go ahead and put your heels flush up against the wall, right? Straight back. Move this trash can out of the way. Okay, now lean over and touch your toes. Whoa! It doesn't work. And the reason it doesn't work is when my center of gravity, my center of mass, is right in the middle, kind of top of hips, belly button, but in the middle. When my belly button goes outside of my toes, now I'm off balance. Now, that's okay. Now, that means I'm going to fall over forwards, right there. Ugh. Okay. Now, when I am flush against a wall, I can't change anything. I can't move to keep my belly button over my feet. When I'm not flush against a wall, take a look at what happens. I lean over and my butt compensates by pushing backwards. My feet are off the wall, but my butt is touching up against it in order to keep my belly button straight over my feet. So that keeps me balanced and means that I can lean. Now, it doesn't feel like I'm doing any leaning, but your body is really good at it. As soon as I start going down, my butt just naturally kicks back to keep my center of mass right over my feet. This is something that we as people don't even think about, but if you've ever watched a kid learning how to walk, it is definitely something that we are not born knowing how to do. We practice it during our first couple of years of life. So if you see like a baby walk, they are really unstable, and they often compensate by like kicking their belly out. They push their belly out so that they can kind of like push like that, because that keeps them a little bit more over their tiny little feet, gives them a little bit more stability. Okay. So that was a nice little center of mass playtime. Let's do another one, which is rotation. So another piece that we can look at is what makes things easy or difficult to rotate. This is called rotational inertia, when something is easy to rotate or difficult to rotate. So there's an example on page 155 right here, that shows as the mass gets closer to the center, it's easier to rotate. We say that we have decreased the rotational inertia by pushing more mass to the center. Yes, so more mass to the center decreases the rotational inertia. So let's kind of do another example of that. So if I stand out here and I put my arms in tight and then I spin back and forth, both looking really cool, and it keeps my rotational inertia small so I can spin really, really fast. You'll notice that when figure skaters are trying to make quick spins, they tuck in really tight. Right? So they'll start out and then they pull in and spin. If I have my arms out like this and I try to do the same spinning, it's harder and I go slower and my arms want to keep going. Once they're in motion, they want to stay in motion because they have a lot of rotational inertia. And I can especially make that true by adding some weights. So if I hold two weights, each about 4 pounds, and hold those out, and then do my spinning, now it's really slow, and it takes a lot more effort to switch directions, right? So the more mass is further out, the harder it is to start rotating, and the harder it is to stop rotating. Okay? More mass further out means tougher to get going and tougher to stop going. Okay. This is also why we pick our feet up when we run. So if you've done sports practices and you've had to do like high knees or butt kickers kind of thing, you want to get your knees in tight when you're going fast, because if you have your legs really long like this and you try to run without bending your feet, it takes a lot of effort to move your feet back and forth, and that doesn't mean that you're going to go very fast. So in order to go fast, you got to pick your feet up, and then they can move back and forth faster. All right, on to page 158 and 159. So for rolling with rotational inertia, we're going to do a little example in class, and we're going to do some predicting. So we're going to skip the rolling for right now. But I do want to talk about rotational inertia in sports. So we talked a little bit about figure skating and how you can put your mass out and then your mass in, and that would decrease your bringing it in decreases your rotational inertia. Putting your mass out increases your rotational inertia. And so if you bring it in, you can spin faster, spin easier. Same deal in gymnastics. If you've seen Simone Biles do some flips, or any gymnast, they tuck really, really tight. And one of the reasons that Simone Biles is really good at gymnastics is that she's very small and compact. A lot of gymnasts are really compact. I mean, Simone Biles is also great at gymnastics because she's practiced a ton and she's very strong and really skilled. But she's also very small. And when she tucks in tight, she gets super duper small. So she can do 3 flips in the air off of one jump, where most people cannot. So in order to do that, she'll tuck crazy, crazy tight so that there's less rotational inertia and she can spin faster. Okay. All right, let's do another example. And we'll do a little example on our rolling mark here. All right, so on the ground, I have a blue spinner. And this allows it to go around like this. It's like a little turntable. I'm going to stand on there. Whew. Okay. I have in my hands 2 weights. Tilt it so that you get a little bit better view. There you go. See the feet. Okay. So here we go. All right, that'll do. Now, if I start by spinning myself around, and I'm going to hold my weights in close. So I'm going to start with my weights in close and start spinning. Actually, I think I'm going to start with my weights off there and start spinning like this. So I'm tight, and then I pull them out, and I slow down. And then I bring them tight, and I speed up. And I pull them out, and I slow down. Let's try it again the other way. So you'll notice when I hit it with the weights, I really slow down when I go out. The weight out makes it much more difficult for me to rotate, and that really slows me down. Okay, so let's summarize some of that, jot a little bit of it down. So let's take a look at what we've got there. Right here. Okay. So first, I was looking at what makes things easy or difficult to rotate. So I found that when I moved the mass to the center, it was easy to rotate. When the mass was far out, it was really difficult to rotate. Similarly, over here, when I brought my arms in, I span really fast. When I put them out, I span slowly, spun slowly, and then I brought them in again and I spun fast again. Okay, so let's talk about the next thing. And the next thing is going to be angular momentum. So we've already talked a little bit about linear momentum. Linear momentum, P, was equal to mv, mass times velocity. Angular momentum is calculated with I times W. So I stands for rotational inertia. That's like a measure of how far from the center your mass is concentrated. So when I put the weights out, I was increasing my rotational inertia, brought them in, decreased my rotational inertia. That's I. Then funny looking W is rotational velocity, which would be like revolutions per minute or radians per second. So if I multiply my rotational inertia by my rotational velocity, I can find my angular momentum. And just like regular momentum, we have conservation of angular momentum. So a large I, like a large hands out, will mean smaller spinning speed. And then bring the hands in, and now I have a smaller eye, and that means bigger, faster spinning speed. Right? Now, I can also do this for things like a spinning wheel, right? So I can get a wheel spinning. It's going to have angular momentum in a certain direction. Then I can use that to flip me the other way. So we're going to kind of end here. I'm going to show you that spinning wheel example, but we've already seen some conservation of angular momentum on the spinner. And then at the end, you're going to do chapter 11 practice problems, numbers 7, 11, 12, 19, 27, 29, and 30, all from chapter 11. And that starts on page 165. So starting on page 165. Okay. So let's do the last example, which is demonstrating how to do some angular momentum using a spinning bike wheel. So here we are. There, lovely. See if I can make that work. All right. So I have a bike wheel here. The bike wheel can spin around. Okay? And we can see it spinning around. It looks nice. So now what I'm going to do is I'm going to get the bike wheel spinning. I'm going to stand on here. Here we go. I'm going to face you and then get the bike wheel spinning. So I'm going to hit it real fast, pushing it down. All right, so now here it is. And now when I flip it, oh, I flip the opposite way. So as I twist the bike wheel's rotational inertia, because it has a heavy tire on the outside, if the bike wheel is going this way, I go the opposite way in order to balance it out. All right, I have to match its rotational momentum with my own rotational momentum. And then I go back to straight. Okay, so I'll try that again. Take it down, get it going, and go to here. Now, if I twist it, I spin the opposite way. And then I twist it and spin the opposite way. And twist and spin the opposite way. So I'm spinning the opposite way of the bike tire, but I'm spinning a lot slower because the bike tire is less massive. Now, my mass is pretty concentrated to the center. The bike's tire's mass is more on the outside, but I weigh a lot more, right? The bike tire is a few pounds. I'm 145 pounds, so not totally a fair balance there, right? But it is kind of neat. And you can even do it by kind of holding it up tight, and you can really feel that shift. So I hold it like this, and then I twist, and boy, does it feel, yep, it wants to go. Yeah. And if you're good, you can even hold it on one edge and let it track around. And I'm only holding it by a finger here. I don't know if you can see, no pressure applied. As long as I spin evenly, the bike tire stays happy. The bike tire's rotational momentum is balanced by mine. Awesome. Okay. So that finishes up chapter 11. Now we're going to hit the chapter practice problems for chapters 9 and 11. Enjoy.